Ну, всем привет. Меня зовут Геннадий. Я уже по-русски не очень могу говорить. Оказывается, что русский мой родной язык. Я родился в Советском Союзе и с родителем, только с родителем уже говорю по-русски. Я сейчас буду, эм, я буду это все делать по-английски. Это будет намного легче мне, но если вы хотите э, вопросы мне давать по-русски, тогда я понимаю. Эм, ну все, давай уже. Это уже очень, только это было трудно для меня. Так, ну сейчас, секунду, это первый раз на этот систем, так я должен, вот, screen share, сейчас, ага, хорошо, вы можете все видеть. Ну-ка, я сейчас буду начинать. Ну, okay, по-английски. So, my name is Jim Kogan. I'll tell you a little bit about my background. I started out interested in machine learning by doing research into recommender systems. So these were systems in starting in the early social media days. People became interested in being able to recommend content to users of the internet. So, for example, for Amazon, of course, product recommendations. You might also like this product, but also in music and art, there were, especially in music, there were new services like Last.fm, which would try to recommend music to you based on your taste. So whatever music that you have already listened to, they would recommend music that you like. And it turns out that that's a machine learning problem. In the early days, this was done entirely using collaborative filtering, which means using just the listener data. So the idea was any two songs that had similar listeners were likely to you could recommend to people. So if you basically try to recommend to music to person A that which other people listen to the same music as person A, you find other songs that they're listening to and recommend them. So entirely based on listening player user listener data instead of using the content, the actual audio. So that's how it was before. More recently, there is work on doing this with the content. Not what my talk is about, though, but this was my early background. This was kind of my interest in machine learning and music. I was kind of interested in music technology and in the world of people working on music technology. There was, certainly there was interest in these scientific and academic applications, like, such as recommending music. But then in that same world, there were many people who were interested in more artistic or creative applications of the same technology. And so I started working with friends of mine to create more creative projects. One was this project with my friend Jeff Snyder, who builds musical instruments, like the one that you see here. This is an electronic, sort of wind instrument, like a flute. And what we did was we designed so that the flute itself doesn't make any sound. It's just a controller. But it has a whole bunch of sensors on it, breath pressure, temperature sensor, and a bunch of touch pads on the fingers. And sort of the idea for this project was to allow somebody to control a digital synthesizer with this instrument. And the way that we do that is to run the synthesizer on the computer and then use the controller to change the parameters of the synthesizer to make it make different sounds. So you can actually hear that here. I'm not sure if you hear my computer sound. It's not as fun. Yeah, so the idea here is that, let's see here. The idea here we can, so we're using a basically machine learning to translate the parameters into or to translate the sensor data, how you're holding the instrument, into parameters for the synthesizer. So, for example, if you're playing a sine wave, it affects the pitch or, whatever other synthesizer parameters that are part of the specific synthesizer. So this kind of made me interested in more creative applications of AI. And I did a lot of projects that like this. This is an early project where I would download many images from Google Images for a specific search, like Valentine's Day. And then I analyze the color distributions of each of those Google image searches to try to get the color of different words or phrases, things that you could search for in Google, using what's called a self-organizing map. So these were all sort of early projects. So for a couple of years, I became interested in new media arts. So this is kind of like not machine learning, or AI, but more like creating artistic installations and musical performances and this kind of stuff. Not exactly science, but it all happened because of my initial interest in creative machine learning. And so I started doing a lot of work with computer vision and projection mapping and this kind of stuff for a couple of years. And then starting in 2015, when deep learning first began to create interesting kinds of images and sounds and text, I went back to machine learning in a more serious way, and I began to work, much more with it. In these slides, I normally explain what a neural network is or what a convolutional neural network, how it works. But because I want to get into my work, I'm going to skip that. If you I guess this is a relatively scientific conference, ML plus art, so I guess people here are probably pretty familiar with it. In case you're not, you can go to this link, to see this demo and to mlforA.github.io to learn more about neural networks. But I'm just going to continue. So I became interested in this line of research over the last 10 or so years in visualizing convolutional neural networks. So starting in 2020, I guess it was around 2012, convolutional neural networks began to basically dominate computer vision. And they were capable of doing image classification very accurately and lots of other sort of feats. And a lot of people became interested in trying to understand a little bit better, like how convolutional neural networks work, what happens inside of them. They are extremely large and opaque. So some people began to research this, and one technique that was developed by these guys in 2013 was to try to send images to a neural network, do forward passes on each of the images, and then save the parts of images which maximally activated a particular neuron. So, for example, this neuron right here on the top left seems to like, stripes. This neuron over here on the top left of the second figure looks for lattices and gates and fences. This looks for people. This one looks for barcodes. And so you could see that the neurons were learning very advanced features, things, high level features like the kind that we described. And that could help us sort of understand, what they were seeing. And then related to this was research starting around the same time that tried to accomplish the same purpose, trying to take a neuron of interest and try to understand what that neuron is looking for, what activates that neuron highly. And this technique would involve, instead of forwarding real images into the network, it would try to synthesize images from scratch and then synthesize them such as to activate a particular neuron. So, for example, if you do this process for a neuron that is looking for faces, you would synthesize a face. And this made big news, I think, 2014 or something like that, when Google made their Google Cat. So they synthesized, this is the sort of like beginning, I think, a few years before Deep Dream, when they synthesized the cat, and this made the news. This cat face here. So now, a couple of years after that, the thing that really got me interested in deep learning was this program, Deep Dream. And so Deep Dream started in 2015, and it was made by three researcher engineers at Google. Alex Mordvintsev, who I think spoke at this before. I think you guys probably know him. And Mike Taika and Chris Olah. They basically took this technique and they developed it to the point that it was able to make much more vivid and colorful and interesting looking images. So, they found, for example, if they could they found a neuron in the neural network that activated for bananas. And so they developed a technique. Alex basically developed a technique for optimizing these pixels so as to make it look more and more to the neural network that it's seeing bananas, or parachutes or screws or so on. And then the twist on this that they called Deep Dream was this. So, the process from before is using optimization. In other words, it kind of optimizes the pixels so as to activate a particular neuron in the neural network. But what they did here instead was, instead of having some neuron that you're purposely trying to optimize, you instead start with a real image, like these gazelles or hartebeests or something like that, and you forward it to the neural network, and you observe all of the activations of the neurons, and then you optimize the pixels so as to make all of the activations go higher. So whatever the neural network sees, whether it sees stripes or dogs or pigs or whatever, basically change the pixels so as to enhance all of those activations, and so this is kind of what happens when you do that, and you get these wild, extremely vivid and psychedelic looking images of these gazelles. And so then Alex began to experiment with this technique. He began to start with images of pure noise, and then just try to dream to sort of synthesize images of this kind, and did a pretty good job with it. As you can see, Mike started working with the same technique. He introduced also, I think, making looping videos, or not looping videos, but feedback based videos, where you could generate videos by just, you start with, you generate one image and then you distort it somehow and then maybe zoom in and then input that to the next generation in order to make the next frame, and you repeat this in a feedback loop. And so he started doing that. I learned all of this from them, and so I stand on the shoulders of giants. They released software for doing Deep Dream, and so what I did was I began to try to introduce some techniques into it that would allow a little bit more. Sorry, one second. Can you? Okay. I have some dog trouble here. So I began to experiment with this technique by introducing masks into the equation. So here the masks would try to allocate one part of the canvas um, to optimize one particular feature, and the other side of the canvas to optimize another feature. So you kind of combine them in interesting ways. So here you see a transition from left to right using with two neurons. So the optimization kind of goes from left to right and gradually fading from one neuron to another. So you could compose with these masks in different ways. This is using like a circular mask. So there's kind of an inside and an outside. On the outside, you have these kinds of flowers, and then on the inside, you have this kind of pattern. It looks a little bit like a flower buzz or something like that. And you can also then generate videos using the technique that I described, using feedback loops and kind of zooming out and so on. And you could make masks out of other kinds of images. So here, this is a mask made out of an eye, and then optimized like so. So then a little while later, I figured out how to generate perfect loops. So these are actually 3-second long videos, and it appears like it never really stops. It's just kind of looping endlessly. Zooming out. So it's a little bit like if you know what a shepherd tone is in audio, it's kind of the same thing except in the image domain. And then I combined this technique with basically neural style transfer. Neural style transfer is a related technique that uses neural networks to synthesize images. That synthesizes images with the style of another image. So, for example, to generate a texture that appears to look like Hokusai's Great Wave off Kanagawa, and so it just goes endlessly this way. Same thing, except Vasily Kandinsky. So Kandinsky over here, just kind of going forever. You probably have a low frame rate in what you're seeing. So if you can see this online, or Google Maps. This is kind of my favorite one. So just Google Maps of your nightmares. Okay, so here these are perfect loops, which are using Deep Dream in different ways. So here you can see that like it's always kind of going, in these striped patterns, or moving around in circles, or you could do portraits. So this is the Mona Lisa on the left, and this is Jan LeCun on the right. Doing texture synthesis of Jackson Pollock, Frida Kahlo, and Salvador Dali. You can see like what look like melting clocks here. Georgia O'Keeffe, who painted flowers. So all of these are also using this technique of neural style transfer, which I just described. So this is kind of neural style transfer in its most basic form, is essentially to regenerate one image in the style of another image. So a content image with a style image, and so this is the Mona Lisa in the style of Starry Night and Hokusai and Google Maps. And so this I've used it as a installation called Cubist Mirror. So this kind of just like lets people see themselves, in these different styles. They get in front of the camera and they can draw themselves, or they can see themselves, restyled into these different styled images. I've also been really interested in generative models. So these are things like generative adversarial networks, GANs, as they're called, autoencoder, variational autoencoders, and more recently things like transformers have become really popular generative models. And generative models are neural networks that generate content. In the other examples of style transfer and deep dream, the neural networks were not generating content; they were kind of being used in this in this kind of nested larger optimization process. But here you have a neural network that actually outputs images or sounds or text, and like cats or TV screens or cars and so on. We'll skip some of this. So the two that were kind of for the most part very popular over the last few years were variational autoencoders and generative adversarial networks. So autoencoders are this neural network architecture which would try to basically learn some low dimensional, high information encoding of a data set, such that the network was able to both learn an encoding and a decoding that would turn these latent vectors back into the same images that were encoded into them. That the encoding came from. So the autoencoder was trying to learn how to regenerate the exact same image, but first going through this encoding decoder architecture where you are able to learn some kind of like some kind of a representation of the data set which captures its most important features. And GANs, generative adversarial networks, work in a similar fashion. They have these two neural networks, a generator and discriminator. It's kind of similar. The generator is similar to the decoder in an autoencoder. It is responsible for turning latent input vectors and generating images out of them. But instead of having an encoder function, you have this discriminator neural network, which is basically trying to tell apart images made by the generator from images in the data set. And we don't have so much time to get into the details. I'm sure most people here are pretty familiar with GANs. But if you're not, just look them up. In 2015, I saw Alec Radford and Luke Metz and Samit Chintala, who generated images, who basically trained images of faces with GANs for the first time. This was late 2015. And so they demonstrated how you could do arithmetic on these features. So you could generate, man with glasses and subtract man and add woman, and you would get woman with glasses. And this was pretty astonishing and very, very much, state of the art in 2015. And I became interested in this project. And so what I did was I trained a GAN on a data set of handwritten Chinese characters from Harbin University. You're looking at actual handwritten Chinese characters. And so I trained the DC GAN on them until I could generate images of these letters. So these are my results. So these are different Chinese characters, and these are GANs trained to generate them. And you could do interpolations between different characters. Right, so these are, interpolations between related characters, and even to the point that they could memorize. If you know anything about Chinese characters, they have these radicals that are highlighted in red here, and that the radicals would be preserved. So GANs have made tremendous progress over many years. By 2018, they were making completely life-size, very realistic looking faces, and to the point that I think in 2020 it's just like life size looking. That's an old slide now. And GANs and more recently a lot of the more visual. A lot of the newer generative models are now using other kinds of architectures. Slowly, transformers are becoming the I think are becoming the most dominant kind of generative model form for at least for making very realistic high resolution images. But regardless, all of them continue to just get more and more realistic. Let me just check my time. So it's 10:40. I guess maybe I can go for another 10 minutes with my slides, and then leave some time for some Q&A. So I'm going to hurry up a little bit on these. So this is some work I did training StyleGAN, which is one of the most kind of user-friendly, let's say, high-resolution generative adversarial networks. I trained it on a data set of 100,000 paintings from art history, basically sketches and portraits. These are these are not images from the data set. These are all generated by the neural network to generate, life-size paintings. So you can see what that looks like. Yeah. Right. And it has remarkable diversity. So it can generate lots and lots of different images. So this is all. So this is all more examples of GANs generating stuff, mixing different animals together. So this is big GAN generating an owl, a dog, and then their combination. So this owl plus a dog. So this owl plus this dog is this animal right here. This is an owl plus a dog, another owl dog, an owl cat. Looks like a snow leopard a little bit. Just different mixtures of owls. The sea lion plus a dog. And this is my favorite. This is a whale, like an orca, plus a tram. And so if you combine a whale and the tram, you get this, which looks a little bit like a ferry, or like a ship, basically. So I thought that was kind of cute. This is more big GAN generation. I'm going to skip this. Let me skip some of this image stuff. This is basically image translations. So generating satellite imagery from maps. So you take a map tile and you generate synthetic satellite imagery. This is from NVIDIA, just showing the state of these things. This is already 2018, so the state of the art is actually much better now. But they could generate videos, like basically video game graphic level detail from these labeled maps. And generating bodies and so on. So if any of you are ever in Berlin, I have an installation that's inside of a museum called the Futurium, which basically allows you to use this technique. This is you basically paint with your fingers on a tablet, and it generates a realistic looking sort of painting, like a photograph of nature. And then the other installation I have there lets you move around these plastic pieces and let it generate a like overhead satellite imagery of the scene. So the blue pieces are water, the green pieces are parks, and the red pieces are buildings. Let's look at this. Then you could also use these image-to-image networks to basically copy faces and do sort of face swapping and what's now called deep fakes. Of course, deep fakes wasn't a term in 2000, whatever this was, 2017, 2018. But basically it, this was kind of the early experiments I did with this. more of this kind of face swapping stuff. Then Glow kind of introduced, sort of it was a model that could get a perfect inverse of an image. And so here I'm able to give myself blonde hair, glasses, heavy makeup, a beard, bald spots, and all sorts of things. And or to change my face into other faces. This is myself being turned into a young Justin Bieber, just for fun. Or being turned into Donald Trump, Vladimir Putin, and Kim Jong-un. So I hope you can see all of that in action. So there, I don't know if any of you saw FaceApp. I think FaceApp was developed by people in Russia. I might be wrong about that. I might be thinking of something else, or maybe Ukraine even. But FaceApp is this application that will put a smile in your face. So it takes this image of me, and it put this smile on. And of course, this isn't my real smile. My smile doesn't look like that. But I thought it would be funny to kind of run this again. I would take this image and I would put it into FaceApp, and then I would run it again and make it smile even more. And so this was so basically, if you run this over and over and over again, it will continue to make your smile bigger and bigger and bigger until it can't see your face anymore. And so then at this point it quits because it can't recognize my face. So and all of that. And then there's more fun things that you could do, like using style transfer to superimpose images into other images. So I started putting myself into the backs of famous paintings. Just kind of like having fun using myself as a subject. Yeah, exactly. And that's all. So the last thing that I wanted to mention, let's see if I have time. It's 10:46. I have a couple of minutes. I'm going to describe a sort of a dream project of mine that I'm beginning to resume research on. So a couple of years ago, when I first learned about Ethereum, which is, the sort of decentralized world supercomputer of sorts, I had this idea to try to create an art program which I called Abraham, which would be the first sort of autonomous artist. And the idea here is, it's kind of a combination of things. So one is that over the last few years, there's been this explosion of interest into AI arts. And so these are all AI artists of sorts. Some of them are friends of mine. And then this kind of, and AI arts has been around for a long time. People working with AI have been interested in making programs that generated artworks and did so independently of them. But the thing that I think was always missing in these projects was an automaton, something that had autonomy or sovereignty or true independence. And the idea that I had was is influenced by the blockchain space, where I first heard of people writing about this idea of art DAOs. And an art DAO is basically a decentralized autonomous organization which produces art and sells art and kind of makes decisions on the art autonomously. And so they describe some, dream scenarios in which this could happen. And I often thought that in art DAO, what the art DAO fixed in the AI art idea was this problem of will. So, when an artist creates a program that uses AI to generate art, it feels to me more like the artist is the human, and the program is like the dummy on the arm of the ventriloquist. And so I wanted to figure out if the ArcDAO idea could could break this connection, could make it so that because it's autonomous, to make it so that it behaves on its own accord. And so the idea I had was to try to create a generative art program whose behavior comes from the collective creativity and input of a network of participants who cooperate together to sort of steer that model. And so basically crowdsourced creativity in a sense. What's going on here? There we go. Yeah. So I kind of turned to nature, for inspiration, how to create, how to make something that demonstrates its own agency. And this is probably a really difficult point to make, especially to make it in someone else's second language. But this is where it gets a little bit, it gets a little bit harder to describe. So for me, the idea that I turned to was the idea of the super organism. So we have this idea that in a super organism, like a collection of bees, or a termite mound, or a flock of birds, you have this idea of collective intelligence, that the collection of these organisms is itself an organism, a super organism as it's called, but one that has its own mind, its own sort of, its own, life force in a sense. It's like these bees have a hive mind. And so my idea was that if you could take the hive mind of humans and direct it towards something creative, you can create some artwork which is the end result of of many people. And that's kind of the purpose and goal of Abraham. So some other analogies are dunes. Dunes are emergent phenomena. A dune is a collection of sand, but really, there's no such thing as a dune. There's just grains of sand. But we ascribe to the collection that has some kind of a form, that it has some property, that it's a dune. And so again, I kind of see autonomy as emerging from coordination of smaller things. So I don't have time to get into all of the technical details, but basically I'll just mention very briefly that the project is actually, I can show you here that the better place to go is this paper, this poster and paper, where I describe exactly what I'm trying to do. And it's basically to try to take a neural network and decentralize it. Make it so that the network, you use multi-party computation and federated learning to essentially turn a neural network into some kind of a shared secret among a bunch of people. So that's kind of the idea. I'm not gonna talk about Abraham that much, except to say that I proposed the project a few years ago, and then I worked on it for a little while, and then I put it down last year. But that I'm about to resume research on it again, and I'm looking for collaborators. And so if it's something that interests you, please do get in touch. So let me skip this stuff, and this is kind of the project is really interesting to me because it also kind of is that these four, it kind of brings together four things that are very interesting to me: computer art, AI, blockchains and cryptoeconomics and decentralization, and the sort of philosophy of mind. And so this is kind of what what I'm going for, more or less. So yeah, the collective imagination is sort of the goal is to model the collective imagination. Okay, so I've also over the last few years, I'll just mention very briefly, I do a lot of educational work, and so I used to run a lot of workshops in uh, in rooms together with people. These days, this is not allowed, so so these workshops have stopped. But hopefully they'll come back in the future. And I started doing more of these workshops online. And I have a collection of materials that has often been called ML4A at GitHub.io. That's where the old website is. It's now located at ml4a.net. So that's actually one of the things that's changed. And lots of demos online. So things, tools that I've made, and instructional guides, and so on. So these are all, and I record a lot of my classes. So you can find all of that at ml4a.net. And lastly, I'm an advisor to Runway, which is an application that makes all of this super easy to use, like an application that lets you run machine learning algorithms on your computer using the cloud, making it super easy for creatives to kind of get into it. So for anyone who's interested in that, please go to Runway. Okay, so that's all I have for you. Thank you very much. Спасибо большое за все. And if you have any questions, есть вопросы, пожалуйста, давай.